sheet 3 should have been titled sheet 2. Just a slight goof up, but we'll start looking at these problems together. Once I'm hopeful that by the time we discuss these problems, we would get a fair deal of an idea of how to use work energy theorem and the basic principles that we have learned in work power energy. Those would come through us. So let's look at the first problem, work power energy sheet 3. Right then, settle down, all of you. I'm hopeful and I'm assuming that you would have at least attempted these problems, at least read through these problems and scribbled your bit here and there, so that my discussions become effective, fruitful and meaningful. All right? So the first problem is about a bob of mass m attached to this point by means of an inextensible ideal string n of length L, and the arrangement is placed at a height 2L above the ground. The bob is held, that is in this position, horizontal position, and is released from this horizontal position, Now, what is mentioned here in the problem is that if the breaking strength of the string is twice the weight of the bob, the weight of the bob is mg, and the breaking strength of the string is 2 mg. That means when the tension in the string becomes 2 mg, the string snaps. When the tension in the string becomes 2 mg, the string snaps. All right. So first, we want to find the position where the string breaks. That's the first thing that we need to address. So this mass m will execute a circular path centered at this point and of radius L. Right? After a while, the mass m in its circular journey swings to this position, and this becomes the position of the string. The string would have tilted by an amount theta referred to the horizontal. Right? Now, this is the vertical position. This is the horizontal position. At this instant, the tension in the string is T. And this is the point where the string breaks. That means this is the point where the tension becomes 2 mg. This is the breaking position of the string, snapping position. T becomes equal to 2 mg. Now, by the time the bob would have swung to this position, it would have acquired a velocity, right? The velocity acquired by the bob would be perpendicular to the radius of the circular path. Yes or no? Would be perpendicular to the circular path. This is the radius at this point. So would be a velocity v at this instant. Perpendicular to the string. Perpendicular to the string, because the string length designates the radius, right? Now the forces acting on the bob. What are the forces acting on the bob? There is mg downwards. There is T this way, 2mg. These are the only two forces acting on the bob, right? Now, if the string makes an angle theta with the horizontal, the perpendicular to the string will make an angle theta with the vertical, yes or no? So this angle will be theta, right? This angle will be theta. Do you realize that the bob at this instant requires centripetal force, right? Who gives it the centripetal force? No, tension minus mg sine theta. Realize that mg has a component in this direction, which is mg sine theta. Tension has a component in this direction, which is mg sine theta, and has a component in the v direction, which is mg cos theta, right? It has a component like this, which is mg cos theta. So T minus mg sine theta becomes instrumental in providing the required centripetal force at this instant, right? So at this instant, T minus mg sine theta becomes equal to, if L is the length of the string, then L would be the radius of the circular trajectory, would be mv squared by L, right? Where this T is equal to 2mg. This T is equal to 2mg. So this T is 2mg. Right? Now 1. Also, notice that the bob in coming to this position would have lost an elevation of this amount. This is the elevation lost, right? In moving from the horizontal state to the state, it would have lost this amount of elevation. This elevation is how much? If L is the length of the string, then this elevation is going to be L sine theta, right? Isn't it? This is going to be L sine theta. So there is loss in potential energy of the bob. How much is the loss in potential energy? mg L sine theta is the loss in potential energy. Where does it appear? It appears as gain in kinetic energy. It starts from rest, 0 kinetic energy, to half mv squared. So gain in kinetic energy is half mv squared. If you look at it from work energy perspective, the same thing will appear, but I still want to write the equation for you because you've just started to learn work power energy. See, when the particle goes from this position to this position, mg acts downwards, right? There is displacement also which is downwards. So what's the work done by mg? mg into displacement in the direction of mg, which is mg into L sine theta, right? Now T and V are always perpendicular to each other. T and the corresponding displacement will always be perpendicular to each other. So tension does no work. Work done by mg is mg L sine theta, yes or no? mg sine theta into L. mg L sine theta is the work done by gravity. Work done by tension is going to be 0. Work done by tension is going to be 0, isn't it? Because tension will always be perpendicular to displacement. See, if this particle, if tension is like this is the circular trajectory, then the displacement ds will always be along the tangent to the trajectory, will be perpendicular to t, and therefore t into ds, t dot ds is going to be 0. So work done by tension is going to be 0, and from work energy perspective, this must be equal to change of kinetic energy, which is half mv squared. Yes or no? Right? Do you all understand this? Now, so we have two physical conditions. One is, this is energy compliance, and this is centripetal force compliance. Yes or no? What we could then achieve out of this is, this mv squared by L we can source from here. mv squared by L, as you can see, is 2mg sine theta. Yes or no? See, mv squared by L is 2mg sine theta, which I can plug into this. right? Right? So 2 mg sine theta plus mg sine theta, 3 mg sine theta is 2 mg. Is 2 mg. I hope all of you register whatever I have done. Sine theta is 2 by 3. Such is theta. This will give me the theta at which the string just about snaps. The string just about snaps, breaks. Yes or no? Is that fine with all of you? So far so good, right? Now, the next part of the problem is, so then, if sine theta is 2 by 3, realize that v squared, plugging in sine theta equal to 2 by 3, is 4g by L. Yes or no? V squared would be 4g by L. 4g into L, I'm so sorry. 4g into L by 3. 4g into L by 3. Sine theta is 2 by 3. 4g into L by 3, that's v squared for the particle at the instant it detaches itself from the string, right? This is the instant when it detaches itself from the string. Now, from this point onwards, what's the story? Can I remove the clutter from here and only retain what is relevant for the problem subsequently? Right? Now, sine theta has turned out to be 2 by 3. Now from this point, that is point P. From this point P, the particle, realize, has a velocity v that makes an angle theta with the horizontal. At this point P, the particle has a velocity v that makes an angle theta with the horizontal. Yes or no? Given by sine theta equal to 2 by 3. How about it? And it's at a certain distance from the ground. How much is this? L sine theta. This entire displacement is 2L. Right? So how much above the ground? 2L minus L sine theta is its height above the ground at an instant when it becomes free from the thread. Right? That means at this instant, 2L minus L sine theta. Right? Oh, so sorry. I'm so sorry. I need to fix this. This theta would be vertical. Right. This theta, I have marked it vertical here. For some reason, since I have placed it here, it seemed as if it's horizontal. Yeah, it's vertical only. It's vertical only. Right. So that's the height above the ground, and this is the disposition of the velocity. At an instant, the particle becomes free. At an instant when the particle becomes free. Now, the v at this instant. So, obviously, you would realize that the particle will execute a projectile trajectory, parabolic trajectory, projectile motion with horizontal velocity vx being v sine theta, the vertical velocity being v cos theta. Right? So, let me find out the time the particle takes to hit the ground. Let me find out the time the particle takes to hit the ground from the instant when it detaches itself from the string, right? So suppose it takes t seconds for a vertical displacement 2L minus L sine theta. So do you realize 2L minus L sine theta is the vertical velocity v cos theta, which is instrumental in providing it the vertical displacement? V cos theta into t plus half gt squared plus half gt squared, yes or no? How about it? Now v is known from these considerations, 4gl by 3, root 4gl by 3. Sine theta is known, so cos theta can be obtained. Sine theta can be plugged in and you can solve for t. You will get two values of t, a quadratic in t, you will get a positive in instant a negative instant. Ignore the negative instant of time that you get, right? Because this is t equal to 0. Whatever happens after this is positive values of t, right? So I don't want you to do the calculations. I want you to just understand this. Solve this quadratic using Sridharacharya. Solve for t, time it takes to hit the ground. Now, if it takes t seconds to hit the ground, suppose it lands on the ground somewhere, then what's the displacement? Suppose it lands at p prime on the ground. Then its horizontal displacement x naught from this position is going to be what? V sine theta into t. X naught is going to be V sine theta into t, right? So x naught is going to be V sine theta into t, where t is obtained from these considerations. Clear? Now from this point the horizontal displacement is this much, but if you have to look at how much from this point, then that's not difficult. Once you know x naught, to x naught you would have to add this amount of horizontal displacement. How much is this? This is L minus L cos theta. L minus L cos theta would be this. So the horizontal displacement from this position where it lands on the ground would be this length plus x naught. Yes or no? So the displacement from the original position is going to be x naught, which is the horizontal displacement from p when it lands on the ground at p prime, plus this length. This length is how much? L minus L cos theta. That's going to be the horizontal displacement from this instant where it lands on the ground. Is that okay or not okay? Okay. Let's look at the next problem. So far so good, right? Nothing difficult about it. So here we have a spring and there is a block, small block of mass m. The spring is in its natural state. This is a natural state of the spring, uncompressed, unelongated, undeformed state. This is a spring of force constant K given by 5 mg by L naught, where L naught is the original length of the spring. This is the original length of the spring, right? That's given. And at this instant, this particle resting on a smooth horizontal surface is imparted a velocity v naught to the right. Okay. Now, we want to find the position where the particle breaks off the ground. That's the first thing that, and then the speed of the particle at the time it breaks off the ground, right? These are the two things that we need to take care of. Pretty simple. See, the spring after a while will assume this state. This becomes a spring. This becomes the particle. And the particle at this instant develops a velocity v. And the spring length, suppose this is theta. This is theta. Then the new spring length will be L naught sec theta. Would be the new spring length. What would be the elongation in the spring? Elongation in the spring is going to be L naught into sec theta minus 1. Final length minus initial length. That's the elongation in the spring. The tension in the spring, the force in the spring would be K times delta L, right? So T is going to be K times delta L, right? Is it not? Realize that this angle is theta. At an instant when it just breaks off the ground, T cos theta must just about become equal to mg. Yes or no? At this instant when it just breaks off the ground, mg is acting downwards, T cos theta is acting upwards. If T cos theta just about becomes equal to mg at this instant, right? T cos theta just about becomes equal to mg, then at this instant, it's on the verge of breaking off the ground. Just to explain things a little more, when it breaks off the ground, the forces acting on it are mg downwards, t cos theta upwards, right, and normal reaction n from the ground, right. At an instant when it just breaks off the ground, what happens to n? N just about becomes equal to 0. That means t cos theta becomes equal to mg. That will designate this instant when it just about breaks off the ground. So when it breaks off the ground, t cos theta becomes equal to mg. What is t? T is k into delta L, right? K into delta L. Delta L is L naught into sec theta minus 1. Into cos theta. Yes or no? T, that's t cos theta. And that must just about become equal to mg, where k into L naught is 5 mg. K into L naught is 5 mg. So this k into L naught can be written as 5 mg. K into L naught can be, and that 5 will come here to make it 1/5. Yes or no? So then we have 1 minus cos theta equal to 1 by 5. I hope all of you realize why I did this, how I did this. See, this KL naught is 5 mg, mg by 5 mg, 1 by 5, and 1 minus cos theta is 1 by 5, cos theta is 4 by 5. Cos theta is 4 by 5. So the theta at which it just about breaks off the ground is given by cos theta equal to 4 by 5. Right? Clear? Now, I want to find the speed of the particle at this instant of time. I want to be able to find the speed of the particle at this instant of time. Now, what are the forces acting on the particle when it goes from, I'll give it to you, don't worry. What are the forces acting on the particle when it goes from this state to this state? And also normal reaction from the ground. When the particle moves across the two states, the forces acting are mg downwards, normal reaction n upwards. Only at this instant normal reaction becomes 0, and there is spring force acting on it, Fs acting on it like this. Yes or no? This is a variable spring force. Why? Because the elongation is changing with theta. So it's a variable spring force that acts on the particle, right? Now, work done by mg is 0. Why? Because displacement is perpendicular to mg. Work done by n is 0. So the only force that is doing work is the spring force. Work done by the spring is always negative of the change in elastic potential energy. Work done by the spring force is always negative of the change in elastic potential energy, right? So we eventually have work done by the spring force is change of kinetic energy. That's work energy theorem. That's classical work energy theorem applied to this situation. Work done by all forces put together. This is the only force, the spring force doing work, and that must contribute to change of kinetic energy. Work done by the spring force would be negative of the change of elastic potential energy. Yes or no? That means work done by the spring force would be final elastic potential energy, which is half k delta L squared minus, what's the initial potential energy of the spring? 0. 0. That's a change in elastic potential energy. This is negative of the change in elastic potential energy, right? And this must be what? Change of kinetic energy, final kinetic energy minus initial kinetic energy, half m into v squared minus v naught squared. Yes or no? Negative of the change in elastic potential energy of the spring is always change of kinetic energy, right? That's one way to look at it from the perspective of classical work energy theorem. The other way you could look at it is, now everything is known to us. Realize delta L is known because sec theta is going to be 5 by 4. Sec theta is going to be 5 by 4, so delta L is known to us, right? we can plug in the value of delta L. K is known to us, 5 mg by L naught. V naught squared is known to us, so we can obtain V in terms of V naught. The velocity at the instant when the particle just about breaks off the ground is given by work energy theorem as demonstrated here. Yes or no? Right? The other way you could look at it is the same equation, but just different people like to look at it differently. It's the same kind of stuff really. See, realize that tension is constantly, spring force is constantly retarding this particle. So it's losing kinetic energy, yes or no? Particle is moving to the right, but component of the spring force is to the left, which is retarding this. So it is losing kinetic energy, right? Loss of kinetic energy is what? Initial kinetic energy minus final kinetic energy, right? Loss of kinetic energy is half m v naught squared minus v squared. That's a loss in kinetic energy, and that must be gain. Where does it go? It manifests itself as gain of elastic potential energy. That means gain is what? Gain is final minus initial. Loss is always initial minus final. Gain is final minus initial. Change is always final minus initial. Change is always. So this is the loss of kinetic energy. It translates into gain of elastic potential energy of the spring, which is the same equation really, which is the same equation. Yes or no? Do you realize it's the same equation as that? It's the same equation. So you can solve for V from these considerations in terms of V naught. Shall we proceed? There is a particle of mass m that falls along this trajectory, curvilinear trajectory, and this trajectory is smooth. Whereas this trajectory is, the straight path is rough and has coefficient of friction mu. Right? It slides on the rough horizontal surface. So by the time it reaches this point, it would have acquired a velocity v. It hits the spring with this velocity and starts to compress the spring. It starts to compress the spring. Now when it compresses the spring, eventually friction on it would act leftwards. The spring force would act in this direction. Both the devils will start to retard the particle. The particle will then eventually come to rest, and when it comes to rest, after having compressed the spring by a certain amount, then that state of the spring would be a state of maximum compression. That state of the spring will be a state of maximum compression. Yes or no? Now, let's say, having done this, it compresses the spring by an amount x. In the process, say the spring gets compressed. This was the original position of the spring. Say the spring gets compressed by an amount x during this. I mean, just to be technically correct with you, let's say the mass was here and the spring was here totally, right? And this compresses the spring by a certain amount x. This compresses the spring by a certain amount x. By the time the spring gets compressed by an amount x, and if this is x max, the velocity of this particle must have got reduced to 0. Yes or no? Now, between this state and this state, I would apply work energy theorem. Between this state, the topmost state, and this final state, the state of maximum compression of the spring, this is x equal to x max. I'm going to apply work energy theorem. Now, work done by gravity is how much? mgh. Displacement downwards, mg downwards. Work done by gravity is going to be mgh. Now, all along its journey from A to B, there is frictional force, which is mu mg acting to the left. Yes or no? Maximum static friction, approximately kinetic friction will act on it in a direction opposite to relative motion. So frictional force will act to the left, whereas displacement takes place towards the right. What's the work done by the frictional force? Minus mu mg into x. That's the work done by the frictional force. And realize that the work done by normal reaction is going to be 0. Displacement perpendicular to normal reaction at all times. Right? Minus mu mg x. What's the work done by the spring force? Negative of the change in elastic potential energy. Its elastic potential energy at this juncture is 0. Its elastic potential energy here is half kx squared. So negative of the change in elastic potential energy is minus half kx squared. That's the work done by all forces put together. Is that not? That's the work done by all forces put together between this state and this final state. Right? And this, from classical work energy considerations, must be change of kinetic energy. But it starts from rest and goes to rest. From rest to rest, change in kinetic energy is 0. Right? When you solve for this quadratic in x, you would get you would get two values of x, a positive x and a negative x. Right? But you're going to take the positive x. Right? Why do I say you'll get two opposite values or opposite signs in x? Because this equation is like half kx squared plus mu mgx minus mgh equal to 0. Yes or no? And do you realize the product of the roots is c by a, which is negative? So one root must be positive, other root must be negative when you solve this quadratic, right? So you're going to reject the negative value of x, and this will give you the maximum, the positive x will give you the maximum compression that occurs in the spring. Maximum compression that occurs in the spring. Okay, that's part 1 of the problem. Part 2 of the problem, what's the work done once you solve for x? What's the work done by friction? Minus mu mgx would be the work done by friction, right? Now, after the spring gets compressed by an amount x, the spring will exert on this a force kx to the left. The spring has got compressed, right? So the spring will exert at this instant a force equal to kx to the left, right? Now, this particle will move to the left only if kx is greater than mu mg. If kx can overcome maximum static friction, then it will move to the left. However, you would find when you solve for x, you would find that kx is less than mu mg, and if kx turns out to be less than mu mg, then the particle will remain stationary even after compressing the spring by an amount, maximum amount x, because the spring force is not enough, will not be enough to overcome maximum static friction, isn't it? The spring force will act in this direction, would want to displace the particle, move the particle in this direction, but frictional force will oppose it. You'll find that kx, after having solved for x, you'll realize that kx is less than mu mg, and therefore the particle will remain stationary. The spring will stay in its state of maximum compression. In its state of maximum compression. This is what would happen. Right? Clear? A vertical rod of mass m is kept on a mass capital M. Okay. Problem number 4 is as follows. There is a wedge of mass capital M and is being acted upon by a force capital F directed rightwards as shown. There is a rod which is constrained to move vertically. It could be in a sleeve. The rod could be in a sleeve which prevents lateral movement. This sleeve prevents lateral movement of the rod, right? The rod is given to be of mass small m. This is the vertical rod and is given to be of mass small m. The angle of inclination of the plane is theta. Now, after a while, the wedge gets displaced by an amount x to the right. The wedge moves by an amount x to the right. We want to find the speeds of the wedge and the rod at this instant of time. You know what I'm saying? Let's understand the problem physically first. see, one thing for sure, this is the inclined plane, right? Now, after a while, when the inclined plane moves rightwards by an amount x, if the inclined plane moves rightwards by an amount x, realize that the rod was originally in this state, right? Rod was originally in this state. Now, what would happen to the rod? The rod would move up, isn't it? This was the point of contact of the rod with the inclined plane, right? This was the point of contact of the rod with the inclined plane. What would happen to the rod? The rod would move up. The rod will therefore move to this position. This was the point of contact of the rod initially. When the inclined plane comes to the state, then this would be the point of contact of the rod with the inclined plane. So, this is x units. This angle is theta. So, very clearly, do you realize that if the plane moves by an amount x to the right, the rod moves up by an amount h equal to x tan theta, isn't it? I can explain again, those of you who are still, h is x tan theta. See, this was the original state of the inclined plane. The inclined plane moves to the right by an amount x. This is the new state of the inclined plane. The rod, however, is constrained to move only vertically, right? So, the rod, while the inclined plane goes from this state to this state, the point of contact of the rod goes from P to Q vertically, right? So, the rod moves up by an amount PQ. PQ is x tan theta. PQ is x tan theta. Do you realize that? So, if the inclined plane moves to the right by an amount x, the rod moves up by an amount x tan theta. Yes or no? Now, not only that, the kinematic constraint, the wedge constraint here. See, the inclined plane has a velocity v1 which is only horizontal. The inclined plane only has a horizontal velocity, right? The rod at any given instant will have a vertical velocity only. Now, in order that they maintain contact, what is the condition for them to maintain contact? Yes, along the common normal direction, they must have the same velocity. Yes or no? Along this common normal, they must have the same velocity, right? So then, v1 sin theta must be equal to v2 cos theta. In this direction, which is the common normal direction, they must have the same velocity, which means v1 sin theta must be equal to v2 cos theta. So, when the inclined plane moves by an amount x to the right, at that instant, the inclined plane has a horizontal velocity v1, the rod has a vertical velocity v2, where v1 and v2 are not independent of each other. They must be connected by this condition, because this ensures contact. This ensures contact between the wedge and the rod. Yes or no? Relative velocity, relative acceleration, relative motion in a direction, common normal direction must be 0. That's what guarantees contact. Clear? Now, when the inclined plane moves to the right, what are the forces acting on the inclined plane? F like this, mg like this, right? External forces. There is normal reaction R from the ground upwards. I will look at a system that comprises the inclined plane plus the rod. Internal force, right? So I would look at, so what they do on each other will not contribute to work energy considerations, right? I would apply work energy theorem between this state and this final state of the inclined plane. I'll apply work energy theorem to a system that comprises the inclined plane and the rod. Now, there is also weight of the rod acting downwards. That's also an external force. Mother Earth, mg downwards, capital Mg downwards, R upwards. These are external forces on the system that comprises the inclined plane plus the rod. Now, let me apply work energy theorem to this entire system. What's the work done by F? F into X? Yes or no? Work done by F is going to be F into X. And by this time, the inclined plane develops a velocity v1, the rod develops a velocity v2, and v1 and v2 are connected by this relationship, right? Then, what's the work done by mg? Small mg. Small mg is acting downwards, and the displacement of this is upwards. So, mg minus mg into h minus mg into h is the work done by gravity, where h is x tan theta, yes or no? Right, so work done by gravity is minus mg into h. H is upwards, which is x tan theta. That's the work done by gravity, yes or no? Work done by capital Mg is 0, work done by r is 0. Why? Because the displacements are perpendicular to capital Mg and r. So no work done, right? And this entire thing must be what? Total change in kinetic energy of the rod plus the plane, right? Change in kinetic energy of the rod is what? Half m small m v2 squared. Right? Change in kinetic energy of the plane would be half capital M into v1 squared. Yes or no? Where you could write v2 here as v1 tan theta, v2 could be written as v1 tan theta and plugged into this equation. v2 is v1 tan theta plugged into this equation, and you can solve for v1, isn't it right? v2 as v1 tan theta, plug into this equation and solve for v1. Once v1 is known, then v2 is v1 tan theta is known, etc. That's all. It's Mother Earth that exerts this force on the rod. It is not at all internal. It is tremendously external. This is the force between the rod and Mother Earth. Mother Earth exerting on both these entities a force which is certainly external. If you include Mother Earth as part of the system, then internal. Only the force that they exert on each other is internal, which is the normal reaction, which may or may not have a direct bearing on the weight. Don't even assume that mg is internal. Mg is certainly external. It's the force that Mother Earth exerts on the entity. It is always external, except when you include Mother Earth in the scenario, it will be deemed internal. Right? There is this chain. These are the links of the chain along this. This is the chain inside a smooth tube. This is a tube and there is a chain like this. As you can see, these are the various links of the chain, right? String, in fact. Two beads of masses m1 and m2. There is a mass m1 connected here. At this end of a string, at this end of the string, there is a mass m1 connected. At this end, there is a mass m2 connected. Now, and they are kept on the at the horizontal diametrical points of a fixed smooth vertical semicircular tube. This is a fixed vertical semicircular tube. If the beads are released from the given position, find their speeds as a function of vertical displacement of m2. Okay. See, what transpires here is this end is closed. This is the open end, right? M2 starts to fall down. M2 starts to fall vertically down, right? Now, up to a certain instant, M2 would have descended by an amount, y say. M2 would have descended by an amount, y say. by this time, m1, see the string length, this string length must be managed by this string length here, right? So while m2 would have gone down by an amount y, this would have covered an arc length y, this would have covered a circular arc y, right? So m1 must have moved to this position. m1 must have moved to this position, covering an arc length y, covering an arc length y. This arc length would have been y. Yes or no? Constancy of string length? Right, string constraint. This is the center O of this tube. This is the center O of this tube. And this m1 would have described an angle theta at this point, right? Now, the amount by which m1, r is the radius of the tube, theta is known. Why is theta known? Because y is r theta, isn't it? Y, arc length is r into theta. Y is r theta, so theta is known to us. How much is theta? Theta will be y by r, where y is the amount that this descends and it's the arc described by m1 in the circular tube. How about it? Do you understand this? Now, this mass m1 would have got raised by an amount r sine theta. This would have gone down by an amount y, right? This length, as you can see, is r sine theta. By this time, m2 would have developed a speed v downwards, right? This is the other end of the string. So do you realize that m1 would have developed the same speed v? Why? String constraint. The ends of the string, this one end and this one end must have the same velocities, same speeds. Otherwise the string length will change. Yes or no? That's a string consideration again. Clear? Now, between the original state and this state, let me apply work energy theorem. Between the original state in which the string was and this state, let me apply work energy theorem. What are the forces that are doing work? Gravity. That's all. Only gravity is doing work, isn't it? Work done by gravity on m2. m2 is going down. Gravity is acting downwards. m2g into y is the work done by gravity, yes or no? On m2. Right? For m1, mg is acting downwards, and between this state and this state, it has an upward displacement r sine theta. Right? So work done by gravity is negative here because gravity is acting downwards and displacement is upwards. So work done by gravity is going to be minus m1g into r sine theta. That's the work done between the two states by forces external forces acting on the system, right? And this in turn must be equal to change of kinetic energy. Change in kinetic energy, as you can see, they start with zero kinetic energy, and by this time they would have developed a kinetic energy. That's the change in kinetic energy. Right? Where theta you can plug in as y by r, theta you can plug in as y by r, and solve for speed v as a function of y. Do you all understand this properly, perfectly? There is a trolley. And the trolley moves with a constant acceleration a prime to the right. There is a mass m, and some Johnny is pulling it Some Johnny is pulling it with a force T. Some Johnny is pulling it with a force T, causing M to have an acceleration A with respect to the trolley. A is the acceleration of small m with respect to the trolley. Okay. And this A prime is the acceleration of the trolley as seen by a ground observer. As seen by a ground observer. Right? We want to find, and what's given is initial velocities of the bodies are 0. They start from rest. Both the bodies start from rest and build up velocities. And mu is the coefficient of friction between small m and the trolley. Mu is the coefficient of friction between small m and the trolley. We want to find the work done by the man. This is the man I have not shown. Right? Work done by the man in pulling the box relative to the trolley, relative to the ground in t seconds from the beginning. T seconds from the beginning. That means when it starts from rest, what's the work done by the man in the trolley frame of reference, in the ground frame of reference, t seconds from start. This is what we need to do. Right? Essentially, hey, look, if I can solve for t, that's the force acting on the particle, right? Now the particle has a displacement from the ground frame, has a displacement from the trolley frame. So work done in the ground frame would be t into displacement of m in the ground frame. Work done by t in the trolley frame would be t into displacement of m in the trolley frame. That's as simple as this, yes or no? So I want to find the displacement of, first of all, I want to find t. I want to be able to obtain the value of t. Look, I can obtain the value of t either using Newton's second law in the ground frame or in the trolley frame. Say if I use it in the ground frame. In the ground frame, what would be the free body diagram of the particle? There is relative motion between small m and the trolley. So friction would be kinetic, which is approximately maximum static, right? And the motion of small m with respect to the trolley is rightwards. With respect to the trolley is rightwards. Yes or no? So now in the ground frame, do you realize that this particle m has an acceleration a plus a prime? Yes or no? Do you realize this? Acceleration with respect to the trolley is a, acceleration of the trolley is a prime. So the acceleration of small m as seen by a ground observer would be a plus a prime. Now why does this happen? This happens because of two things. This is the effect. What's the cause? The cause of this acceleration is t acting to the right and friction would be leftwards and it would be approximately maximum static, mu mg, precisely the case. That's a free body in the ground frame of reference, yes or no? Which gives me t minus mu mg. T minus mu mg is mass into acceleration. This is the cause. The effect is m into a plus a prime. So t therefore is known. T is mu mg, the tension in the string, the force with which the man is pulling small m. T is mu mg plus m into a plus a prime. Clear? Yes or no? That's t obtained. I could have also obtained t by looking at the free body of this in the trolley frame of reference. Same t. Let's see. Now in the trolley frame of reference, trolley frame, what are the forces? This is an accelerated frame, right? In the trolley frame, realize that of course there is t, which is a real force acting to the right. There is mu mg acting to the left, and and there is pseudo force which would be ma prime leftwards. Right? And the net effect of all of this, see, if I apply the pseudo force, I will get the acceleration of small m in the trolley frame, right, which is given to be a prime, which is given the trolley frame, the acceleration is a prime. The moment I deploy the pseudo force, then the effect produced would be in the trolley frame, which is the non-inertial frame. Yes or no? Oh, sorry, a is the acceleration in the trolley frame, right? So this will give me the same value of t. What would it do? T minus mu mg minus ma prime is m into a. Realize that I get the same value of t whether I use the ground frame or the trolley frame. Either way, I'm going to get the same value of the force that the man applies on the particle small m. Clear? So far so good? Now, having said this, having obtained the value of t one way or the other, can I wipe this off? So far so good, right? Now, in the ground frame, what is the acceleration of this? A plus a prime is the acceleration of this, right? In the ground frame, that's the acceleration of small m, right? What's the displacement s? S would be initial velocity 0, half of a plus a prime into t squared in t seconds. That's going to be the displacement of the particle in t seconds as seen in the ground frame. Yes or no? Initial velocity is given to be 0. So what would be the work done by t in the ground frame? T into s, because t is acting to the right, displacement is to the right, so work done by t is going to be t into s. Is going to be t into s in the ground frame. Now let's look at the work done in the trolley frame. In the trolley frame, that means now I will have to look at displacement with respect to the trolley. So in order to obtain displacement with respect to the trolley, I will have to look at acceleration with respect to the trolley, right? So what's the displacement with respect to the trolley now? Half of at squared is the acceleration with respect to the trolley. This will give me the displacement on the in the trolley frame of reference, right? Which then would mean work done by t in the trolley frame, work done by t in the trolley frame is going to be work done by t in the trolley frame is going to be t into displacement in the trolley frame, t into displacement in the trolley frame. Clear? No problem, right? Let's examine problem number 7 then. Clear? There is an inclined plane . Height of the inclined plane is h. The inclined plane is given an acceleration a to the right. It's given that a is 3g by 2 and theta is 45 degrees. That means, you know, if this is h, this will also be h, isn't it? Because theta is 45 degrees. Now, this surface is smooth and there is a particle of mass small m on this surface. There is a particle of mass small m on this surface. Okay. Now the objective of this problem is when the trolley moves to the right, this moves up, and this comes to this point after a while, and it leaves the, see, the velocity of small m with respect to the inclined plane would be along the plane. Otherwise, it would have lost contact with the plane, right? Yes or no? So by the time small m reaches this point, it would have had a velocity vrel with respect to the inclined plane. It would have had a velocity vrel with respect to the inclined plane, which would be parallel to the inclined plane, isn't it? Because if the relative velocity was perpendicular to the inclined plane, anywhere during this journey, it would have lost contact, right? Now, I want to find vrel. I want to be able to find vrel. Clear? What I do is, I look at small m in the inclined plane frame of reference. When I look at small m in the inclined plane frame of reference, what are the forces acting on small m? There is clearly mg downwards. There is normal reaction perpendicular to the plane like this. Yes or no? And if the inclined plane has an acceleration a to the right, then the inclined plane frame of reference, which is a non-inertial frame, there is going to be a pseudo force small m into a to the left. Yes or no? Tell me. Tell me if you're convinced about all the forces. These are the real forces, mg and n. So this is all the description in the inclined plane frame of reference. Non-inertial. So if you look at things in the inclined frame of reference, then in addition to the real forces mg and n, you would have to incorporate, depict, delineate a pseudo force which would be opposite to a. ma leftwards. If a is to the right, it's going to be ma to the left. Yes or no? Sounds good? Sounds all right? Now, between this state and this state, I'm going to apply work energy theorem in the inclined plane frame of reference. Between this state A and this state, when it's about to leave the inclined plane, their vrel is not the absolute velocity of the mass, it's the velocity in the inclined plane frame of reference. Between states A and B, I want to apply work energy theorem in the inclined plane IP, inclined plane frame, which is the non-inertial frame. This is what I want to be able to do. Right? Now, when the particle goes from A to B, with respect, all the displacements therefore would also have to be taken with respect to the trolley. All the displacements would have to be taken with respect to the trolley, right? Sorry, I'm so sorry. IP, inclined plane. I've been saying trolley all along, is it? I'm so sorry. The inclined plane. Trolley in the shape of an inclined plane, if you like. Why not? Right? So then, in the inclined plane frame of reference, so all the displacements would have to be taken in the inclined plane frame of reference, okay? So mg is acting downwards all along. In the inclined plane frame of reference, when the particle goes from A to B, the displacement in the inclined plane of reference, plane frame of reference is h upwards and mg is acting downwards. What's the work done by gravity? Minus mg into h, right? H, this. I'm sorry, this. Minus mg into this h, right? Now, there is pseudo force acting to the left, ma, right? And when the particle goes from A to B, in the direction of pseudo force, what's the displacement with respect to the inclined plane? H leftwards, yes or no? What's the displacement in the direction of ma? H to the left, as seen by the trolley, isn't it? As seen by the inclined plane, inclined plane equal to trolley. Okay? In the inclined plane, with respect to the inclined plane, the horizontal displacement, that means displacement parallel to ma, when the particle migrates from A to B, is going to be h to the left. So what's the work done by ma? MAH. Perfect. Very good. MAH. That's the work done by the pseudo force. Right? And what must this be? Change in kinetic energy with respect to the inclined plane. Some trolley bhoot has come into me. With respect to the inclined plane, the velocity with respect to the inclined plane at this juncture is vrel. The velocity with respect to the inclined plane at this juncture is 0. So change in kinetic energy in the inclined plane frame of reference is going to be half m vrel squared. Yes or no? Right? Can I remove the clutter from here? A is 3g by 2, right? So this will become mgh by 2. A is 3g by 2. Plug in A equal to 3g by 2. This will become mgh by 2, isn't it? Plugging in A equal to 3g by 2. This will become mgh by 2. That's half m vrel squared. So this gives me vrel equal to root gh. Yes or no? Right? That's the velocity of the mass at the instant it's about to detach itself from the inclined plane. Right? Here I get it right. Velocity with respect to the inclined plane at an instant when it's about to get detached from the inclined plane.
What would happen if I took the ground frame of reference?
Then you will have to apply, you will have to take all this. First of all, you are not going to take pseudo force, right? You will have to apply work energy, all the displacements in the ground frame of reference is what you need to do. But it doesn't make sense here, right? Now, from this point onwards, let's see what's going to transpire. But so far, so good, right? Have you registered all the basic ideas delivered here? Right? You have? Minus the trolley aspect. Okay, now, having said this, see, this is vrel. At B, this is vrel. At a height h. Right? And all of this is 45 degrees. Right? So relative velocity in the vertical direction vrel by root 2, vrel by root 2 horizontal. Relative velocity vertical and horizontal with respect to the inclined plane. So with respect to the inclined plane, if I resolve it, right, all of these angles are 45 degrees. It will be VREL cos 45 degrees, VREL by root 2. VREL by root 2 is the horizontal and vertical velocity, right? Now, what's the velocity of the inclined plane in the vertical direction? Velocity of the inclined plane in the vertical direction is 0. Yes or no? Which means the relative velocity that you see of the particle in the vertical direction is not just the relative velocity in the vertical direction, but is also the absolute velocity in the vertical direction. Yes or no? Because the inclined plane has no motion in the vertical direction. So the relative velocity in the vertical direction of this particle is actually the absolute velocity in the vertical direction. Yes or no? Right? So in the ground frame, even in the ground frame, the velocity in the vertical direction is going to be, in the ground frame, the velocity of this particle at B is going to be VREL by 2, VREL by root 2. Yes or no? Because the inclined plane has no vertical motion. VREL by root 2 means root GH by 2, etc. That's the Vy. That's the Vy at B. That's the Vy at B. Clear? Now, can I remove all of this? B, the point B is at a height h above the ground. At B, the particle has a vertical velocity Vy, absolute vertical velocity this time Vy, which is root GH by 2, and has a horizontal velocity Vx, which is different from VREL by root 2, because the trolley has a horizontal motion, so it has Vx, but we don't care about this too much at B, right? Now, the maximum height that the particle goes above B is going to be Vy squared by 2g. Yes or no? Maximum height the particle reaches above B is going to be Vy squared by 2g. So the maximum height above the ground that the particle reaches, h max, is going to be Vy squared by 2g plus h above the ground. That's the maximum height that it reaches above the ground, where Vy we've already obtained as root gh by 2, etc. Yes or no? So there is a horizontal region there is spring here, there is a mass m here, there is the spring of stiffness K, mass attached at one end of the spring, and the mass is compressed by the mass compresses the spring by an amount x. So this is a state of compression of the spring. There is elastic potential energy in the spring. So there is this bullet which is shot in this compressed state, and it escapes the tube at P with a velocity v. Escapes the tube at P with a velocity v. And this height is given to be h above the ground. We want to be able to model around h, which will give horizontal range of the bullet a maximum, which will make the horizontal range of the bullet a maximum it could be. Right? That is what we want to be able to do. Now, when it's compressed by an amount x here, there is elastic potential energy half kx squared in the spring. In fact, when it's released from the state, this amount of energy is released by the spring onto the mass m, right? If you look at it from work energy perspective, then the work done by the spring force is going to be half kx squared minus, when it comes into the state, in a relaxed state, elastic potential energy is 0. So this is the work done by the spring force from a state of compression x to its natural state 0 compression, right? This is the work done by the spring force. Now, if I go from this point A to this point P, between A and P, if I have to deploy work energy theorem, between A and P, if I have to deploy work energy theorem, this is the work done by the spring force, right? And by the time the spring releases this mass, the mass would have developed a velocity v naught. So this is at the behest of the spring force. So half m v naught squared is half kx squared. So I know v naught. I know v naught at the instant of release. I know v naught at the instant of release. V naught is known from these considerations. Yes or no? The compression of the spring which is released manifests itself as kinetic energy at A when it enters this tubular region, right? Now, between this point when it has a velocity v naught, the spring is now in its relaxed state. So don't have to bother about the spring, right? Between A and P, I therefore deploy work energy theorem. The only force acting on the particle between A and P is gravity, downwards. What's the downward displacement of the mass? Mg into capital H minus small h, right, isn't it? The loss in elevation is capital H minus small h. So can I say Mg into capital H minus small h? That's the work done by gravity. And that must be change in kinetic energy, half m v squared minus v naught squared, half m v squared minus v naught squared. Yes or no? Right? Which then makes v available to us, right? Because half m v naught squared is actually half kx squared, which I can transpose here, and I end up getting half m v squared is mg into capital H minus small h plus half m v naught squared. Half m v naught squared is half kx squared. Right? X of course is a fixed quantity. X of course is a fixed quantity. Now when it goes from P, it has a velocity v, which is given by these considerations, It, once it jets out of this tube with a velocity v, it's free to move under this projectile trajectory, parabolic trajectory, right? It has to fall through a height h. The time taken for it to fall through a height h would be how much? What would be the time it takes to fall through this height h? Right? Root 2h by g? Root 2h by g, yes or no? See, to fall through a height h, when it goes to this position, h would be half gt squared. So time taken would be root 2h by g? Yes or no? Right? So time taken is root 2h by g. Now, the range accomplished in the process is going to be v into t. The range accomplished is going to be v into t. Yes or no? I need to then obtain a value of small h for which r is maximum. I want to maximize r by selecting h, small h, appropriately and suitably. This is what I want to be able to do. That means maximizing r is the same as maximizing r squared. Maximizing r is the same as maximizing r squared, yes or no? Now the physics part is over. It's just the algebra which has to be gracefully managed. Just gracefully managed. R squared t squared. T squared is 2h by g. T is root 2h by g. So t squared is going to be 2h by g into v squared. V squared, realize, is 2g into h minus small h, right? 2g into h minus this m and this m will get cancelled, plus k by m into x squared. Yes or no? Do you realize what I've done here? T squared is 2h by g and v squared is 2 into this divided by m. So m and m will get cancelled. So 2g into h minus h, mm etc. gets cancelled, plus kx squared by m, kx squared by m, right? That's v squared. I need to maximize this. I need to select a value of x for which this is going to be a maximum, yes or no? Right? Can I just remove the clutter from you? Do you all understand everything that I have been doing here? Now, if I allow small h to penetrate, this is what I get. Precisely. Very good. Excellent, Raj. So nice. Do you then take cognizance of the fact that in order to maximize r squared, I need to maximize this. I need to actually maximize this. This expression, just look at this expression. Don't bother about the rest. This expression is going to be, or I can just simplify the algebra, I can divide this and mg, right? Clear? So I rewrite just this expression. I don't have to bother about this too. This expression could be looked upon as minus 2h squared plus h into 2h plus kx squared by mg, isn't it? See? H into kx squared by mg plus 2h. This is the expression to be maximized. This is the expression to be maximized. Right? Now, can I just remove the diagram? It's not needed anymore. See, it's like minus 2h squared plus, this is some constant, say b into h, minus 2h squared plus b into h. This I want to maximize. B is that constant. I want to maximize. Yes or no? I want to maximize this expression. Clear? This expression is like minus 2 into h squared minus b by 2 into h. See, I took minus 2 common, h squared minus b by 2 into h, which is like minus 2. I complete the square, h squared minus 2 into b by 4 into h plus b squared by 4, b squared by 16. I hope you realize what I have done here. 2ab plus b squared by 16, so that this becomes a perfect square. I added this so that this could become a perfect square, and then I need to adjust plus, rather plus b squared by 8 I need to adjust. I hope you realize why. Minus 2 into b squared by 16, that's b squared by 8 I need to adjust because this was never there. This was never there. Clear? Which is like b squared by 8 minus 2 into h minus b by 4 whole square. Yes or no? b by 4 whole square. Now do you realize that this is always a non-negative number? So this would always be less than or equal to b squared by 8. This expression will always be less than or equal to b squared by 8. That means the maximum value of this expression will be b squared by 8. Right? The maximum value of this expression would be b squared by 8. Maximum value of this expression E, max E, is b squared by 8. And when does it happen? This happens when this is 0. H is b by 4. When H is b by 4. When this is 0, this will become b squared by 8. That means when H is b by 4, yes or no? Where b we chose as this. Yes or no? Do you all understand this? So at H equal to b by 4, where b is this, the range obtained is going to be a maximum. In that expression for range, plug in H equal to b by 4 to get the R max, Clear? Where b is this number. Just to simplify the algebra, I chose this way. Right? Once I teach you quadratics, I will not do so much. I'll just draw the graph and I'll show you that if it's a downward opening parabola or an upward opening parabola, and I'll readily do that for you. Right? Once I've taught maxima, minima to you, I would differentiate and with respect to H and show the same. Right? But since I have not covered all that, I just want to go from first principles and do the needful for you. Right? Is that all right? So there is sand here. There is sand here in this region. And there is a nail that descends from a height h. There is a nail that descends from a height h. The mass of the nail is small m. And the nail, that means this point P, penetrates by an amount x. P reaches P prime and it penetrates by an amount x into the sand. We want to find the average resistance of the sand and the time of penetration of the nail into the sand. That means this time taken to cover this length, time of penetration in the sand. Okay. The first thing that I want to do here is, let's say the resistance offered by the sand would be upwards F. Let's say F is the average resistance offered by the sand and it's going to be upwards, yes or no? So that F will act on the nail upwards during this penetration regime, right? And during this entire journey from P to P prime, mg is acting downwards, right? So between P and P prime, I'm going to deploy work energy theorem. Between P and P prime, I'm going to deploy work energy theorem. Classical work energy theorem. So mg has been acting downwards all along. So mg into h plus x. That's the work done by gravity. And now, during this journey, F is upwards, x is downwards. So what's the work done by the resistive force? Minus F into x precisely. Minus F into x. It started from rest, ended up being at rest. So change in kinetic energy is 0. So this then is the case, right? This gives us F, the average resistance, as mg into h plus x by x. That's the average resistance offered by sand. That's the average resistance offered by sand. Yes or no? Now, during this journey from Q to P prime, there is F acting upwards, there is mg acting downwards. So F minus mg is the net upward force acting during this journey from Q to P, right? This is the net upward force. This by m is going to give me what? The retardation during this journey. This is going to be the retardation from Q to P. Yes or no? F minus mg, which is gh by x. Therefore, gh by x. gh by x. Yes or no? See, I hope you realize that F minus mg. So mgx will get cancelled. So mgh by x divided by m, that's gh by x. Clear? So that's the average retardation during this journey from Q to P prime. Now, the velocity at Q is root 2 gh. Yes or no? The velocity at P prime is 0. So the time taken from Q to P prime is going to be V equal to A into T. Yes or no? Right? So T then, the time taken from Q to P prime is going to be V, which is root 2gh divided by A. A is gh by x. That's the time taken for the penetration. Yes or no?